In this section, we'll look at extensive form games. Extensive form games are sequential games in which agents play actions one after each other, which is different to normal form games where actions are played simultaneously. We'll look at how to calculate strategies and the Nash equilibria for extensive form games using a technique known as backward induction, and we'll also look at how to solve these games using multi-agent reinforcement learning. After this section, you're expected to be able to identify situations in which extensive form games are a suitable model of a problem, define the strategies and Nash equilibria for an extensive form game, manually apply backward induction to small extensive form games, design and implement backward induction to solve medium-scale extensive form games automatically, and design and implement multi-agent reinforcement learning algorithms to solve extensive form games automatically. Let's get started. Let's look at the following game, which is a normal form game called the buyer and seller game. In the buyer and seller game, there's two players, a seller who's trying to sell a product, a buyer who's trying to buy a product. The seller can manufacture either a high quality product or a low quality product, and the buyer can choose to buy the product or not buy it. If we solve this using our theory from normal form games, we can see that the seller has a dominant strategy to sell low quality products because they will get a payoff of 3 instead of 2 if the buyer buys it, because it will cost them less to manufacture, and they'll get a payoff of 1 versus 0 if they don't sell it, because it will still cost them less to manufacture. The buyer doesn't have a dominant strategy. They would prefer to buy a high quality product at the same price than a low quality product. However, because we know the seller's dominant strategy is to sell, we can eliminate the row for the buyer and determine that what will happen is that the seller produces a low quality product that the buyer never buys. And this is the Nash equilibrium for our game. So the incentive then becomes for sellers to manufacture low quality products and for buyers not to buy them. And this isn't a great situation for anybody, because a much better outcome is this top left. Similar to the prisoner's dilemma, if each agent acts self-interestedly, then they end up with a worse outcome than if they acted globally optimally. But actually, this isn't what happens in real life. Even if this is a toy model of a problem, it's still a model of buying and selling products. Why is this the case? Well, it's because people can usually assess the quality of products before they buy them. So for example, what they can do is go into a shop and look at items. They could return items for a refund if they find it's lower quality than what they thought, or they could go and read reviews about that item. So effectively, sellers have to play their move before buyers, rather than simultaneously like we see in a normal form game. So in reality, the real game would look more like this. In the top right corner here, we have an extensive form game. In an extensive form game, the players take actions sequentially rather than simultaneously. If we look at this game, we can see here that at the top node, a seller has a move where they can choose between to either sell high quality products or low quality products, and then it becomes the buyer's turn who can choose to buy or not buy. This model of the game, sequential games, are called extensive form games, and they form what we're going to talk about in this part. Let's go through a definition of an extensive form game before we look at how to solve it. As we can see here in the top right, an extensive form game can be represented as a tree instead of a matrix as we did in normal form games. We're going to look at perfect information games. Just as in normal form games, perfect information simply means that all of the players in their game are aware of each other, the moves that each others have, the outcome of all of the moves, and the final payoffs of all of the paths through the tree. This is as opposed to imperfect information games where, for example, parts of the state of the game might be hidden. A perfect information extensive form game is a tuple, G, with the following elements. N, which specifies the number of players that are in the game. S, which is the state space of the game. The definition of a state space is the same as in a Markov decision process. The states are represented by nodes in our tree. S0, which is the initial state, which we circle here, is the root node of the tree. A, which is the actions that are available to players. T, which is the transition function that determines what happens in a state, which state it comes to afterwards, same as we've seen earlier in MDPs. P, which is a function that determines which player has the move in the current state. And R, which is the rewards we get at the end of an episode. The main difference between an extensive form game and a Markov decision process is the fact that there are multiple agents in the game. We can see this in the definition of the tuple and the elements. First, we have a number of agents in the game, whereas the Markov decision process assumes there's only one agent in the game, or perhaps more accurately, there might be multiple agents, but there's one agent that controls all of those agents, has control over all of the actions. However, the action function is slightly different in that it tells us the actions that are available to each player in a state rather than just to one individual player. The transition function is the same as before. However, we have this additional function P. P is a function that takes a state and returns the number of the agent whose turn it is at that state. So this means that at each point only one agent can possibly take a turn. Finally, the reward function is also slightly different. As before, it takes a state, but instead of returning just a single real number, it returns a tuple of real numbers, one for each player. In some text you read this may be called U instead of R, referring to utility, but in this we're going to use R to be consistent with the rest of the reinforcement learning literature. Typically in an extensive form game, we only receive a payoff in the final state of the game rather than as states throughout. However, we can model receiving rewards along the path as well by just simply summing them up and specifying the cumulative reward at the end. The model's the same. In an extensive form game, we have the same assumptions as for a normal form game. All of the agents are rational and therefore able to calculate the best strategies for each other. They're all self-interested and they don't care about the payoffs of each other. The game is perfect information, meaning the payoffs are known. The transition function is common knowledge between all the agents. The only difference is we don't have simultaneous moves in this game. So how do we solve perfect information extensive form games? We can solve it using a technique called backwards induction. I'm going to illustrate how backward induction works and illustrate some of the key concepts in extensive form games using the buyer-seller game in extensive form. So in this case here, we can see that we have a game where each player gets exactly one move, but the seller gets to go first. We solve this using backward induction by starting at the bottom of the game in order to solve it. And what we solve is each sub-game of our game. At the bottom of the tree, the sub-game is the final moves that we have for each player and the payoffs that they will receive. First, all we do is solve each of these sub-games. So let's have a look at these two sub-games that we have at the bottom here, where the buyer has to make a choice and determine what we think the buyer would do. In this notation, the buyer has their payoff in the second element of the payoff tuple. On the left sub-game, the buyer has to make a choice between buying and not buying. If they buy, they'll get a reward of 2. If they don't buy, they'll get a reward of 1. Clearly 2 is better than 1, so the buyer is going to select to do this. What we then do is we backpropagate the outcome of this game up to this node. Effectively, we know that if the buyer is rational and self-interested, the outcome of the game at this point will be 2-2. We can do the same for the other game, the other sub-game. In this case, buyer number 2 should prefer to not buy because they'd rather get a reward of 1 instead of 0. So we'd say this, and again, we backpropagate the rewards up to this node here. Because at this particular point, if we assume the buyer is rational and self-interested, we know the outcome of the game is going to be 1-1. So now that we've solved those two subgames, what we can see is the next layer up is another subgame that determines which choices a seller should make. Because we've propagated up these values using our backward induction here, now we need to do is make a decision over which choice would a seller take between these two outcomes, 2-2 and 2-1. Clearly the seller is going to prefer to get a reward of 2 instead of a reward of 1, therefore they're going to choose to make a high quality product. Again, we backpropagate this value up to here, and what we see at this root node now is that the final outcome of the game will be 2-2 if both players are rational and self-interested. So you can see here the backward induction is the idea of solving each subgame at the bottom and recursively solving the subgame above it until we reach the root node. So a few bits of terminology that are important here. The first one is the terminology of subgame, which we've already covered. The second is the idea of the equilibrium path of this game. The equilibrium path is a path from a root node down to one of the final nodes that specifies the move that each player will make at each point, and this becomes our equilibrium. In this case here, this path is our equilibrium path. Assuming all the players are rational and self-interested, the seller will choose high, the buyer will choose buy, and that becomes our equilibrium path. A somewhat related concept is the concept known as subgame perfect equilibria. Which we abbreviate as just SPE. The subgame perfect equilibria of a game consists of all the strategy profiles for all of the agents, such that for any subgame of that game, the strategy for the player that's playing at that node is the best response for that player. So the subgame perfect equilibria is not just the equilibrium path on here, but also includes this strategy that we have here of the buyer not buying should they come into this state here. So in other words, what we have as the subgame perfect equilibria is the strategy that each player would play for each subgame. So therefore, backward induction is simply solving each subgame starting from the bottom, and then using the outcome of that game to solve its parent game. At each point, we're just solving the game that's at one node. In a subgame perfect equilibria, it must be that the strategies that we have, these ones here, constitute a Nash equilibria in every subgame. An interesting note is that if we have a two-player zero-sum game, backward induction gives the same result as the well-known minimax algorithm. If you don't know what that is right now, don't worry about it. But what we're effectively saying is that backward induction is a generalization of the well-known minimax algorithm. Minimax won't work for more than two players or for non-zero-sum games, but backward induction does. But if the game is two-player, non-zero-sum game, then the solution will be the same as minimax. Now we're going to look at an example called the advertising game. You might remember this as the advertising game that we saw in the normal form game section. In that game, the equilibrium was such that firm 1 didn't advertise and firm 2 did. This gave us the outcome 7-13 for firm 1 and 2 respectively. But what if, for example, firm 1 had had a chance to advertise before firm 2? Would this change the outcome? Let's have a look at the game and what it would look like in extensive form. In this exercise, try to solve this extensive form game using backward induction and see if we get a different outcome than we did in the previous game. Okay, so do we get a different outcome? Let's have a look at how to solve this using backward induction. I'm going to start with this subgame here, and I'm firm 2. My payoff is in the right hand tuple. Do I not advertise or do I advertise? Not advertising gives me a payoff of 7 and advertising gives me a payoff of 6, so I'm not going to advertise. That's going to be my subgame perfect equilibria. And I'm going to backpropagate the value 13 and 7 to this node. Now I'm going to solve the second subgame over here. Firm 2, do I not advertise or do I advertise? Well, advertising gives me a payoff of 13 instead of 12, so clearly I'm going to select that. That becomes my subgame perfect equilibria for that game, and the outcome is 713. Now I solve this subgame for firm 1 by using the back propagated values. Does firm 1 prefer to receive a payoff of 13 for advertising or 7 for not advertising? Clearly they're going to advertise and get a higher payoff. So this becomes our equilibria, and the outcome of the game is 13-7. So we can see here this changes the outcome of the game, which previously was that firm 1 didn't advertise and firm 2 did. So by firm 1 taking the first action, they actually gained an advantage. Note that going first isn't always an advantage of a game. Determining, for example, where to attack and telling your opponent before you attack is usually a disadvantage. So sometimes going first can be an advantage, but that's not always the case. Now let's apply the idea of backward induction to a slightly larger game, or at least part of a game, of the game called Tic Tac Toe, otherwise known as noughts and crosses. I'm only going to solve part of the game because the entire game would be too difficult to solve in a simple video and wouldn't fit onto the screen. But we're going to look at the start state where we're in this current game. Down the left here we have whose turn it is at each step, and the moves that we have, we've omitted the names of the moves, but you can see the moves here. For example, X is placed into this spot here, resulting in this new state. I'm going to solve from this state and show that from this state, player X has a dominant strategy that can win the game. Each of these states here also has a subtree, but I'm just going to show you that taking this move leads to a situation where X can always win, and no matter what nought does, they can't win. Let's have a look. So first we're going to start by solving the subgames at the bottom. The subgames at the bottom down here are quite simple because there's only one outcome. We're filling in the last possible spot. So in this case here, the subgame just has one action available. So we're going to back propagate the value of that to the node above it. That's pretty easy back propagation because there's only one action available. And those three actions are the subgame perfect equilibria for those subgames. Now we're going to solve the subgames that are available to nought at this level, of which there's two, this choice and this choice. So in this subgame, player nought can choose between a draw, payoff of 0, or a loss and a payoff of -1. It's going to take the draw if it's rational and self-interested. And in this subgame, it's going to choose between a draw and a payoff of 0, or a win and a payoff of 1. It's going to take the win, clearly, so the payoff will be like this. Now we have several subgames we've got to solve across here for player cross. These subgames here I'm not going to solve. I'm just going to show you that if agent nought takes this move down to here, it will win. If it takes this move down to here, it will win. If it takes this move down here, it will win. So there is a dominant strategy for each of them, and we'll back propagate those values. While there are other moves, just to keep for time, I'm going to do this. This subgame here is a bit trickier. We've got a choice of three actions that we can take, playing here, here, or here. The one on the left leads to a win and a payoff of 1. The one in the middle leads to a drawing game, and the one on the right leads to a loss. So therefore cross is clearly going to take the win, which would be this one here. And we back propagate that value 1, -1. From each point we see here that all the actions that are available to nought have the same outcome, that they end up in a loss, 1 -1 across here. So at this point, once we've reached this state, there's no way that nought can avoid losing, provided that cross plays its game properly. So in this subgame, it doesn't matter which action we take, we just got to propagate our value up and pick one of the subgames as our equilibria, and we get this outcome. And Similarly, what we're going to say, if we solve these games here, it doesn't actually matter what the outcome is going to be, because at best they're going to give a reward of 1 to player cross, and it's going to choose one of those actions. So the outcome is going to be 1 minus 1. And again, we'll just choose this game as our sub-game, perfect equilibria. So what we can see here is that we use backward induction to prove that from this particular state, if player cross takes this move, they end up in a position where they can win the game irrelevant of what naught does. The difference between this game and what we've seen previously is that we've got multiple levels here, but the process is exactly the same. We solve the sub-games at the lowest level, backpropagate the outcomes of those sub-games to the next level, and then we solve the sub-games at that level. And we keep going backwards up until we reach the root node of our game, which is this here. You can try and solve the entire Tic Tac Toe game using this, manually if you like, and what you'll find is that neither player has a strategy to win the game at the start. The best both of them can do is to draw the game. Backward induction is a model-based technique. We need to know the transition function in order to solve this backwards. But we can solve extensive form games in a model-free manner or a simulation-based manner using reinforcement learning. We define a stochastic game as something that's quite similar to an MDP, except that the set of actions, the transition function, and the reward all operate on tuples, just like we saw in an extensive form game. We won't go into detail in this video about the definition of a stochastic game. You can refer to the notes for that. But we will look at the intuition behind how we can use reinforcement learning to solve stochastic games. We can visualize a stochastic game in a similar way to what we visualize an Expectimax tree. Here we see an Expectimax tree earlier from the multicolor tree search notes. We have a state, we can make choices between actions. If we choose an action, there's some probability of going to different outcomes, and then from those outcomes we can choose further actions. In a stochastic game, instead of the outcomes of the actions being chosen probabilistically by the environment, we can model that the outcomes of the actions are in fact chosen by other agents. In this case, the actions with the primes on it refer to the actions that are available to an opponent in a two-player game. So in this case here, action A is chosen by our agent, coming to a new state called L. The dark states refer to the states where one of our opponents has a choice. Our opponent can choose this action A or this action B. From the perspective of the agent that chooses here, the light-colored agent, whether or not another agent chooses this outcome or not is largely irrelevant to how good an action this is. If we sample these enough times and we find that this agent selects this action 80% of the time and this action 20% of the time, then this is the same as the environment choosing it at 80% and 20%. The expected reward can't be calculated based on probabilities because at this node here, the agent that makes the choice between A prime and B prime is making the choice strategically. It's also trying to maximize its expected discounted cumulative reward. So therefore, from the perspective of the player that chooses here, it has to consider the strategy of the player that chooses after it, and in fact, all of the players that choose after it in this move when it's evaluating the strength of move A. But nonetheless, we can see some similarities between MDPs and stochastic games. In this case, the agent has to choose between A and B, and the outcomes that matter are these states for A and these states for B. It's actually largely irrelevant which action this agent chooses from the perspective of this agent. All that's relevant is the outcome that we get to. Whether or not this outcome is selected by another agent or the environment, we can still use reinforcement learning techniques to solve it. Multi-agent Q-learning is a multi-agent version of the well-known Q-learning algorithm. We can see the algorithm itself here on the screen. There are a few differences, notably that instead of getting an MDP as input, it gets a stochastic game with multiple sets of actions for agents and multiple reward functions. What we want to do is learn a Q function Qj for player J, which is the agent that we're learning for. We initialize this arbitrarily like normal. Then multi-agent Q learning looks very similar to standard Q learning. We have a series of episodes. We then select actions using a multi-arm bandit algorithm, execute those actions, wait to see the outcome, and update our Q function. The primary difference is in these three steps here. The first thing we have to do is when we execute the action, instead of observing the state S' that we arrive at, we wait for the other agent's actions, either by simulating them if we're using a simulation environment, or via letting them play their moves if we're using a completely model-free environment. We then observe the rewards that we received over all of those steps that all the other agents made. So we can receive a reward for playing our move, but we might also receive a reward, positive or negative, when an opponent plays one of their moves. And we also observe the new state that we arrive at, which is n moves later, where n is the number of players that take their moves. Then the update rule looks pretty similar. We're updating Q of j, where that's our Q function. We do it by updating the old information plus the weight of alpha times by our new information. And our new information is exactly the same, except we have to remember to sum up all of the rewards we received since we played that move. Note that the temporal difference value is st plus n, which is the state we observe after we have waited for all the other agents to play their actions. So this is effectively exactly the same as Q learning, except instead of executing action A and then observing the new state, we have to wait for all the other agents to play their move, observe that state, and then use this rewards that we received along that path to update our Q function. Multi-agent learning works quite well. However, we can improve things by being strategic about the way we simulate opponent moves. So as we can see here in this example, when we take the selection A and execute it, we wait for the outcome. However, if we're in a simulated environment, how would we simulate an opponent's moves if we don't know who that opponent is? There are a few different strategies we can use in order to simulate a good opponent that will improve our learning. The first strategy that we can use is to just do random selection. This is quite easy because we don't have to think too hard about what our opponent's going to do here, and we just select uniformly between A and B. While it's easy, the problem is it may end up exploring a lot of actions that will never be taken by a good opponent, and therefore we'll get a very poor idea of what a good Q value is for action A and action B. So for example, if a really good opponent would only ever choose action A, but we simulate that the opponent will choose action B 50% of the time, and B is a really good outcome for us, then we'd get a really poor idea of what action A is. The second thing we can do is use a fixed policy. So we can use an existing stochastic policy that gives reasonably good behavior of the opponent. So for example, this could be a hand-coded version of the opponent or a policy we've learned from a similar game. If we use a hand-coded fixed policy, we could determine that action A is a really strong policy for this agent, and therefore we'd simulate this more often than we'd simulate the weaker action B. And this will give us a better idea of what the true Q value for action A is. Of course, this is difficult because if we already have a really great policy for our opponent agent that's been handcrafted, presumably we can usually come up with a very good hand policy for our own agent, and this would defeat the purpose of using reinforcement learning at all. So usually a handcrafted policy or a fixed policy is a reasonably good policy but not a great policy for the particular stochastic game we're trying to solve. And we can use Q learning in order to determine a good policy for this player. The third type of strategy we can use is called self-play. Using self-play, we can simultaneously learn a policy for both ourselves and our opponents. And when it comes time to choose actions for our opponents, we use the policy that we're learning. If the action spaces for both ourselves and our opponents are the same, such as in games like chess and Tic Tac Toe, we can actually learn a single policy and have both our own agent and our opponent's simulated agent use that policy. This is a technique used by, for example, AlphaZero for learning how to play Go. chess, etc. If the action spaces aren't the same, then we actually have to learn separate policies for each of the agents. At this node, we would use the policy for agent J, for example, and this we would use the policy for agent K. But the important thing is that the better that we can simulate the quality of these moves for our opponent player, the better our primary policy, which is the one we really care about, is going to be. Just as we could extend Q-learning or SASA to a multi-agent case, we could also extend Monte Carlo tree search to a multi-agent case with just a small change in our algorithms. Multi-agent MCTS is similar to single-agent MCTS, but we simply modify the basic MCTS algorithm as follows. Recall that the first step in MCTS is the selection step. In the selection step, we have to select a node to expand in our tree. At each point, we choose an action based on the current policy that we have using stochastic multi-arm bandit algorithms. When we select for our moves, we can use our policy in order to select this. But similar to when we are waiting in multi-agent Q-learning, we have to also select for our opponent agents. We can do this using opponent simulated play that we saw in the previous video. That is, we could either select randomly, which isn't going to work very well, but it's very easy. We could use some sort of fixed policy to choose for our opponent, or we could use self-play. In multi-agent MCTS, we know which player's turn it is at each point, and what we have to do is use a multi-arm bandit algorithm to choose an action for that player, irrelevant whether it's us or one of our opponents. The second step is called the expansion step. When we're expanding a node, we would come to this node, which is our node here, and select one action randomly. This would lead us to a node that's a choice for one of our opponents. Unlike in single-agent MCTS, where we then choose an outcome probabilistically, all we do is simulate from this node, get the outcome of the simulation, and backpropagate the value. We don't bother choosing an outcome from one of our opponent states. However, on a subsequent iteration, we might select this node, which has no expansions. Then what we do is randomly choose one of our opponent's actions. Okay, and this will lead to an outcome that might be, for example, a state where we have a move, and we simulate from that. So in other words, different to single-agent MCTS, where we would choose an action and then expand one of the outcomes, all we do is choose the action, result in a state, and do a simulation from there. In future iterations, we effectively simulate the outcomes of our opponent's actions by selecting these nodes, expanding them, and simulating further. The next step is to do the simulation. This step's much the same as before. We simulate a random simulation from the most recently expanded node. The only difference is that we have to remember that the rewards we receive are going to be a vector of rewards, one for each player, and so we have to update the right Q function using the right reward from that vector. The final step is the backpropagation. The backpropagation step is the same as before, except we have to keep the value of each node for every player if we're using self-play. So in other words, we don't just update the Q values for the player that we're learning for, we update the Q value here for player K and also for player J, which is our player. This allows us to then use this Q function for the selection steps in the next iteration. An interesting application of reinforcement learning as applied to extensive form games, in this case imperfect extensive form games where some information is hidden, is the poker play that was written out of Carnegie Mellon University. This is an interesting application because unlike Go, where the game's fully observable, poker has some unobservable parts of the game. For example, the cards that our opponent are holding and the deck of cards that are here. Further to that, we have situations where players can do things like bluff about what cards they have in their hand. What was interesting about this application is the way they used abstraction to solve the game. So when they took their original game, and this triangle here represents, for example, the game tree that they would have to solve, it was far too big to solve using something like backwards induction. What they used was an abstraction algorithm that extracted down to a smaller game. So for example, one of the simple abstractions they used was when you have to bid the amount of money you're prepared to bet. This could be a number in dollars up to a certain amount. And what they did was just bucket those numbers together. So instead of having an action for betting $1, $2, $3 all the way up to the maximum bid, they just bucketed them together and said bets between $10 and $15, for example, are effectively the same. They used several other more sophisticated abstraction algorithms, but in the end you have this smaller game that we're going to solve. They then used a custom algorithm for finding the Nash equilibrium of this game. However, this game, despite being much smaller than the original, is still far too big to solve using backward induction. This custom algorithm used a lot of Monte Carlo simulation techniques in order to come up with the Nash equilibrium for this game. Unlike solutions like Go, for example, though, they actually did find a Nash equilibrium, and they had certain guarantees around the accuracy of that equilibrium. What they did then were able to take that Nash equilibrium and reverse it such that this Nash equilibrium was a valid Nash equilibrium for the original game. This agent was highly successful. It was able to successfully beat some of the world's best poker players. And interestingly, if you go and watch some of the videos, you learn that the player that they derived, the algorithmic player, was successfully able to bluff or lie about what cards it might have in its hand in order to fool its opponent. There was no explicit instructions given to the agent to learn how to lie. It simply did it by noting that sometimes, if it made a really strong bet even though it had poor hands, that was enough to make its opponent decide not to play a bet at all. In this case, this agent wins. This is quite incredible when we think about the fact that just using techniques such as Monte Carlo tree search and the concepts of Nash equilibrium, we're able to not just calculate players that can beat some of the best players in the world, but also to learn strategies such as bluffing. Note, however, that this strategy, like the AlphaZero strategies, requires a lot of computational power and time to train. Much more than the computation that's available to most organizations. In this section, we introduce the notion of extensive form games, which are more or less multi-agent Markov decision processes that can be generalized into something called stochastic games. We learned about backward induction, which is a model-based technique for solving extensive form games that finds the sub-game perfect equilibria of each sub-game and then uses that to solve the parent game. Backward induction is model-based, but we can use model-free and simulation-based reinforcement learning techniques to solve extensive form games as well. We looked at multi-agent Q-learning and multi-agent MCTS. So these techniques can be improved by making informed choices about good opponent moves, such as using self-play. Most importantly though, we saw that multi-agent reinforcement learning techniques are very similar to their single-agent versions, requiring just small modifications to successfully solve extensive form games, but often these require a lot more computational power to solve successfully.